Hi guys, welcome back to the channel. In this video I will be covering the kinetics topic of the A-level chemistry curriculum. So let's begin. So starting with the collision theory, what you need to know is the definition of activation energy first. So that's the minimum energy. So it's the minimum energy required to initiate a reaction. So without the activation energy, a reaction can't begin. And the collision theory states that for a reaction to occur, particles must collide with enough activation energy, so they must at least have this minimum energy to initiate a reaction, as well as colliding with the correct orientation. So even if they have the right activation energy, if they're not in the correct orientation, the reaction won't go ahead. So again, most collisions don't lead to a reaction, as particles don't collide with the activation energy or the correct orientation. So both of these factors must be in there. So both of these factors must be included for a reaction to occur. So they must collide with the activation energy and they must collide with the correct orientation. Okay, so the Maxwell-Boltzmann distribution. So this is basically a graph which shows the distribution of energies that a gas molecule has at a particular temperature. So it'll vary at different temperatures, and that's why we have to mention that it's a particular temperature. And so the curve basically shows, so that's the Maxwell-Boltzmann distribution curve, and this shows that no particles have zero energy. So you might be asked, why does the graph not start at zero? So from the origin, you would say that because no particles have zero energy, so particles have to have some kind of energy to be able to move around. And moving on, so the area under the curve, so all of this area shows the total number of particles, and the peak, so this area here is the most probable energy. So it's the most likely energy that a particle will have, and the average energy of particles is slightly to the right of the peak. So it's not the same as the most probable energy, because this would be the case if the graph looked like this. So if it was symmetrical, but as you can see, the graph is slightly leaned towards the right. That's why the average energy is slightly towards the right of the most probable energy, as you can see in this case. And the area under the curve to the right of activation energy, so this is the activation energy, and the area under the curve right of that shows the particles which have energy equal to or greater than the activation energy. So these are the particles that will lead to the successful collisions and lead to a reaction. Okay, so these are the effects of temperature change. Just learn that, learn this whole table, because you need to know this very well for exam questions, because these come up a lot. So if we're talking about what happens to the curve, so how the curve moves in response to the different increase or decrease in temperature. So if you increase the temperature, the graph would move slightly to the right. So in this case, as you can see, comparing it to the lower temperature graph, so the lower temperature graph is a lot steeper, and the higher temperature graph, because it will cover the more particles will cover the activation energy which is there. That's why the graph becomes less steeper, so it moves to the right. Whereas if you decrease the temperature, the graph will move to the left, so the curve will move to the left. And then the average energy of particles, so because you're increasing the temperature, we'll be coming on to that later, but they will have more energy because they'll be moving around faster. So, and that's why increasing temperature leads to increase in the average energy, whereas a decrease in temperature leads to a decrease in energy. And so now the most probable energy of particles, so if you increase the temperature, the most probable energy increases. So in this case, this is the higher temperature. So as you can see, and the lower temperature has its peak there, whereas the higher temperature has its peak there. So it has a higher energy, so that's why the energy increases. But if you're talking about the number of particles with the most probable energy, as you can see, the lower temperature has this steeper curve. It has a much higher peak in this case. So the number of particles with the most probable energy, if you increase the temperature, would decrease, because if you're looking at the number of particles, it has decreased. And so the activation energy, well, if you're increasing or if you're decreasing the temperature, the activation energy is still the same, and because you're not doing anything to the activation energy, you're not lowering it, you're not doing anything, which a catalyst might do. So in this case, this stays the same. And finally, the number of particles with the activation energy, I've got it wrong in the table, and it's the other way around. So if you increase the temperature, the number of particles with the activation energy increases, and if you decrease the temperature, it would obviously decrease, because as you can see in this curve, and this is the activation energy, and the black line, the black curve, is the higher temperature. So there's a bigger area, and area indicates the number of particles. So there's more number of particles under the curve, under the activation energy curve. So that's why the number of particles with activation energy increases if you increase the temperature. Sorry for the mistype. Alright, so the effect of temperature on the reaction rate. So the rate of reaction is basically the change in concentration of a reactant or product over time. Make sure you mention over time, because that's what makes it a rate. And this is a key definition that you need to learn. It can come up. And so increasing the temperature would increase the average energy of particles as the particles are moving faster, and that's why there will be a higher frequency of collisions, because the particles are moving faster, and that's why they will more likely to have collisions, and more particles will have collisions with energy which is greater than the activation energy, and therefore the number of successful collisions per second increases. And a small increase in temperature leads to a large increase in rate of reaction. This is because when you increase a temperature, it increases both the collision energy, so increase the collision energy, so the energy that the particles collide with, as well as increasing the frequency of collisions, because the particles are moving much faster. So just increasing the temperature has these two factors involved, and that's why it leads to a kind of double effect, and that's why having a small increase in temperature leads to a large increase in rate of reaction. Right, so the effect of concentration, which is usually in solutions, and pressures, which is usually in gases. Okay, so increase in concentration or pressure leads to an increase in rate of reaction. This is because the number of particles per unit volume increases. And this means that the frequency of collisions also increases, and that's why frequency of successful collisions increases as well. So just to illustrate, for example, if you have a box, and let's say you have 5 particles in there, but you have another box which is much smaller, and if this has also 5 particles in there, obviously this box is more likely, the particles in this box are more likely to collide, and that's why lead to a successful collision. That's why if you're increasing the pressure, that's why the rate of reaction is likely to increase. Okay, so catalyst now. So catalyst is a substance which increases the rate of a chemical reaction and without being chemically changed. So when you use that, it will, when you start it at the start of the reaction, it will end up being the same as when you end the reaction. So you'll get the same substance. So the substance will be unchanged at the end of the reaction. And this provides an the catalyst work by providing an alternative reaction route. So alternative reaction route of lower activation energy. So this is a question that commonly comes up. So remember that catalysts work by providing an alternative reaction route which has lower activation energy. So for example, in this picture, so if a catalyst is being used, so the curve isn't moving anywhere, but the activation energy, so before it was there, but after the catalyst it has moved there, so more particles now, because remember the area under the curve is equal to the number of particles. So in this case there were only this number of particles, but then when the activation energy has moved, there's a lot more particles, and that's why there's more particles now under the section which has at least the activation energy, and that's why more particles will lead to a successful collision and therefore a reaction, therefore increasing the rate of reaction.